For part A, this says, show that when you apply the 8-bit 2's complement procedure to the 8-bit 2's complement for negative 128, you get the 8-bit 2's complement for negative 128. So first of all, let's compute the 8-bit 2's complement for negative 128. The absolute value of negative 128 is positive 128, which in 8-bit binary representation is 100000000. So next we need to flip all the ones to zeros and zeros to ones. So that's going to be 0 and then everything else is a 1. And next we need to add 1. So 1 plus 1 is 1, 0. So all of these are going to be zeros, and I'm going to constantly be carrying ones. At the very end, I'm just left with a 1. So since we have a leading 1, this 8-bit 2's complement is really negative 128. So now you can see that the 8-bit 2's complement of a negative 128 is negative 128. So if we plug this back into this process, you can see that the 8-bit 2's complement procedure applied to the 8-bit 2's complement for negative 128 is the 8-bit 2's complement for negative 128. So this is the answer for part A. So for part B, this says, show that if A, B, and A plus B are integers in the range 1 through 128, then 2 to the 8th minus A plus 2 to the 8th minus B equals 2 to the 8th minus the sum of A and B plus 2 to the 8th, which is greater than or equal to 2 to the 8th plus 2 to the 7th. So we know that A, B, and A plus B are integers in the range 1 through 128. So this means that A and B are at least 1. We also know that the sum A plus B is at most 128. And if both A and B are at least 1, and both A and B are at most 128, then that means that they're actually both at most 127, since they have to both add up to a number that's at most 128. So even though in the directions it says A and B are numbers between 1 and 128, we can infer that because A plus B is at most 128, that means A and B are both at most 127. This also means that A plus B has to be at least 2, since A and B are both at least 1, even though it says in the directions that A plus B is in the range 1 through 128. So the first equality is pretty obvious. It's just a matter of rearranging the terms and putting parentheses around certain things. So this is the commutative and associative properties at play. But the inequality is a little bit more difficult to show. So 2 to the 8th minus A plus B, if we look at this subtraction here, we're taking 256, or 2 to the 8th power, and we're subtracting A plus B. The most we could be subtracting here is 128. So this is greater than or equal to 2 to the 8th minus 128, which is 2 to the 7th. And that's because the most we could be subtracting here, to get this as low as possible, would be if A plus B equals 128. And this is equal to 2 to the 7th times 2 minus 1, which is just 2 to the 7th. So now we can just add 2 to the 8th on both sides here, and we get exactly what we wanted to show. Next, it says, explain why it follows that if integers A, B, and A plus B are all in the range 1 through 128, then the 8-bit 2's complement of negative A plus negative B is a negative number. So if we find the 8-bit 2's complement of negative A or negative B, they're guaranteed to be negative numbers, and so we have a specific process for finding the 8-bit 2's complement of a negative integer. And in that process, we have to compute 2 to the 8th minus A and 2 to the 8th minus B, and we have to add those two things together. And we're going to get a number that is at least as large as 2 to the 8th plus 2 to the 7th. And when you write that in binary representation, the 2 to the 8th plus 2 to the 7th is going to have a leading 1, which means that the result is going to be a negative number. And that's why. Thanks, everyone, and I'll see you in the next video.